Hi everyone, happy to be here. My name is Thomas and I'm from the XRP Ledger Foundation, as Max just introduced. This presentation will be a kind of an anecdotal story of my journey with graphs and what I've learned during that journey. I'm not a data scientist. My background is actually in graphic design, but I have spent several years now working with different kinds of data and data-driven design. In the last couple of years, I have worked using graph to combat and prevent criminal finances on the XRP Ledger blockchain. So before we begin, just a brief introduction to the XRP Ledger. It is a decentralized blockchain focused on payments. It launched in 2012 and has to date closed more than 75 million ledgers and 2.5 billion transactions, with ledgers closing every 3 to 4 seconds. Ledgers are basically what other blockchains refers to as blocks. A bit oversimplified, the network consists of accounts and payments, and any account can send a payment to another account, settling in seconds, typically within a single ledger. It's a pseudo-anonymous blockchain by nature, as all transactions are publicly viewable, but no one knows who owns which accounts. In late 2018, a developer in the XRP Ledger community released a ETL sample, fetching all transactions from the blockchain and inserting them into Google BigQuery. Suddenly, having easy access to all transactional information in an easy-to-access format opened a lot of opportunities. It was suddenly possible to learn about the use of the blockchain, the accounts, activities, and much more. My fascination with graphs started from visualizations. I had occasionally seen beautiful visualizations, and I figured a great way to use a BigQuery dataset was to visualize the relationship between the accounts on the XRP Ledger. Searching for tools to accomplish this, it led me to Gephi, a powerful piece of desktop software to analyze and visualize connected data. So the quest began, writing queries for BigQuery to extract information about the 50,000 most active accounts and their payments to formats I could import in Gephi. I quickly found that not only was Gephi a great tool for visualization, it was actually great to analyze connected data, running algorithms, filter the data, and get immediate visual feedback. Visual learning at its finest. This graph, this visualization was the output using a modularity algorithm to find and color communities, sizing the individual nodes based on centrality, visualize payments as the relationship between the nodes. Still, my fascination with graphs was centered on visualization, and sticking to visualizing only a subset of the entire XRP ledger was not enough. It was time to go full scale. The idea was to visualize the entire blockchain, aggregating all the payments into one relationship with metadata such as count and sum. And by using BigQuery to export this data and a script to process the output, this resulted in a dataset of 1.4 million nodes and 2.6 million relationships. To no surprise, in hindsight, it was simply unworkable. This huge dataset in a visual in-memory tool on a 2.9 gigahertz MacBook Pro just not gonna happen. However, with the Gephi toolkit, it was actually possible to work with a headless script. So dusting off my Java, I managed to write scripts to import the data, run a modularity algorithm, and running a Force Atlas layout with approximately 2.5 thousand iterations on an Amazon EC2 compute instance. And the usefulness of visualization in this size is arguable, but the goal of visualizing the entire network was reached. And I learned quite a lot from this initial journey. Tools like Gephi are awesome for analyzing and exploring smaller data sets, but of course it has its limits. Most of what you can visually deduct from a visualization, you can actually read from the data directly. For example, the holes that appears in this graph and the nodes centrality. You'll always be analyzing yesterday's news if you have to extract a snapshot, import it into some database and analyze it. So it was time for me to start looking for alternatives. After researching and testing a range of graph databases, I finally settled for using Neo4j for the next experiment. At this point, largely because of the excellent documentation and the great built-in browser, within a day, I had a database running with the data from the BigQuery dataset, 34 million nodes and 66 million relationships. But despite the ease of creating this database, it was limited to the transformed data that already existed in the BigQuery dataset. So instead of the ETL detour of moving data from the XRP Ledger through BigQuery and import it into the database, it would be much better to go directly from the XRP Ledger and into the database. So first up, I defined the model of the database. And that should include all the accounts and all the successful payments and all the account activations. Just to explain account activations, the XRP Ledger has a sort of anti-spam mechanism built in that require accounts to be funded with a minimum of amount of the native currency in order to be activated and usable. And this mechanism creates a sort of ancestry between accounts. Second, I wrote scripts to first backfill from an XRP Ledger database dump, followed by subscribing to ledgers, closing and inserting data in regular intervals. The approach of the script was pretty straightforward. Decode the data, transform the data, and insert it into Neo4j using Cypher queries. The result was a database of about 45 million nodes and 90 million relationships, all created within days and kept in sync every 15 minutes. Most surprisingly to me at the time, this was manageable on a completely normal laptop compared to working with a graph 30 times bigger in Gephi. This initial database became my playground for experimenting with the Cypher query language, optimizing them, learning how to use the basic algorithms and much more. Some of the most fascinating things coming from a traditional database was being able to write a simple query and have almost immediate output of a visualization of the shortest activation or payment path between two accounts, outputting entire subgraphs or showing the ancestry in several generations from an account. It was also the beginning of using this data to follow the money and getting involved with investigating how and where money moved from scams and fraud. After adding some intelligence to the database of known accounts used by exchanges, it was suddenly quick to get data on payments related to specific exchanges. Using Cypher to extract data about payments sent to, from, and between about 80 of the biggest exchanges, I could produce a chart in an attempt to show indications of market trading sentiment. Running the database for more than half a year, it was time to go bigger. In the most simple form, the XRP Ledger is just accounts and payments, but there is much more to it than that. For example, the XRP Ledger was the first decentralized exchange with support since 2012 for issuing and trading currencies. A transaction can be a payment, but it could also be a trade offer. The final model looks complicated from the classic Neo4j schema visualization, but it's actually quite simple. The backbone of the new model is very simple. We have ledgers, transactions, affections, and ledger objects. The XRP ledger closes a new ledger every 3 to 4 seconds. A ledger contains any number of transactions, and transaction is sent by a ledger object. A ledger object can be received by an object and can also affect an object. Constraints are added to these nodes, which are then further divided into subtypes using multiple labels. Transactions and ledger objects are divided in types by adding an extra label. Some of the benefits of adding multiple labels to nodes are being able to share constraints and indexes for all nodes, but making focused index for smaller sets of data. I also made the decision to go all in and graph everything that could be graphed from the XRP ledger. In this random example, an offer create transaction was included in ledger 16 something million. It was sent by the account beginning with RH5. It affected the account beginning with RK5J, likely the balance changed. It affected the sending account itself. It also affected some offer objects. In other words, an account created an offer to sell one currency for another, which filled an existing offer, and the balances of the accounts was updated. No new offer object was created, so the offer was immediately filled. Or more simply, in this example, a payment transaction was included in ledger 30 something million. It was sent by the account beginning with RJB1. It was received by the account beginning with R2NT. It affected both accounts as their balance changed. It should be pretty simple to do this, as it was just the same as the old database, but only bigger. It turned out to be more challenging than anticipated. It turned out, when digging through the data, that only 15% of the transactions sent on the XRP ledger is actually payments. So moving from only including successful payments to including failed transactions, quickly added up to billions of nodes instead of millions. So with a lot of trials and errors, hotfixes, start overs, and months of work, the final process ended up like this. From XRP Ledger database dumps, which is approximately 2.7 terabytes of data, and at this point in time, 53 million ledgers, binary decoding the data, transforming the data, multiple ledgers in batches in parallel using Node.js worker threads, writing the data to CSV file, repeating from where the dumps ended from a live node to get everything, post-process the CSV file for data deduplication, import it to a clean database using Neo4j admin import, post-process data after import using APOC periodic iterate, run scripts to insert new data as ledgers close, which is every 3 to 4 seconds using Cypher transactions. While this database is actually still running smoothly on its third year, staying completely in sync with the XRP ledger, I'm already running the next generation because the usage of the blockchain increased and the data set is growing rapidly. And because I learned a lot from both importing and using the data from the first design. So for the next slides, I'll be sharing some of the learnings I made during this journey and how the next database has decreased rapidly in size more than halving the storage requirements and halving the number of nodes. It is much easier to write Cypher queries and pass data as parameters, but it is a time hog. So if you start from a clean sheet with a new database, you can use the Neo4j admin import feature. Make sure that the data is clean. It is easier to fix it in the transform phase than later, and you don't want any duplicates in your data. Make sure you escape your quotes. Don't use backslashes, use double quotes. If you import properties with multi-line text, don't. It is way too expensive. So make sure you replace all the new lines in your transform phase with characters you can replace in the database afterwards. You have to pick an ID type with the Neo4j admin import. So for my case, where ledgers have an integer ID, I had to add a pseudo column with a string version of the integer. If the column is not named, it's not imported into the database. You can't use multiple IDs for the same node type. In my case, I'd like to create relations based on account addresses in some cases and based on an account index hash in other cases, but you can't. Oh, and Neo4j admin import is fast, depending on your hardware, of course, but this was months of cyber inserts that was inserted using this in a matter of hours instead. When inserting new data using Cypher, it's easy to merge things, make conditional changes, and so on. But when importing it straight from CSV files, it might leave some unfinished business to be completed after the import is done. Use APOC periodic iterate if you need to process large amounts of data after it's imported. It can even run in parallel. In this example, I'm re-establishing the new lines from the CSV import. You can also combine it with other features, for example, to decode and process JSON strings. Oh yeah, and remember to do this from the command line using Cypher shell to avoid the timeouts you'll run into in the browser. After working with the dataset for a long time, I realized that many of my decisions to explode data structures to graphs only added clutter. For much metadata, you'll probably never need to query it directly, so consider storing some of the metadata as JSON strings instead. If you need the data in a query, you can use one of many APOC functions to deserialize the data on the fly. And if you figure out at a later point that you needed it as a part of your graph, you can choose to refactor the graph using APOC periodic iterate. What you need to store and how all depends on your specific use case, but don't store more than you need. I decided to go all in the first design, and whenever a ledger object was modified, I stored the information in a separate node. Partly, this was because relationships could not be indexed in Neo4j at the time, and partly this was because I wanted to be able to see the property state of any object at an earlier point in time. When developing the new model, I decided to move away from an affection node and instead using relationships directly, and also limit the number of properties to only include the changed properties. For example, a payment modifies two accounts, and the balance of each account is changed. Instead of storing the complete object state, I decided to store only the previous balance and the updated balance on the relationship itself. Indexes are tricky and doesn't always do what you expect. For example, composite indexes could not be used for index-backed order in earlier versions of Neo4j. Indexes are mainly beneficial to do initial queries and not to filter subgraphs such as the relationships to a node. Indexes and constraints will both affect startup and warm-up time, memory consumption, and how long it takes to insert new data. And especially because of the added write workload, if you are establishing a new database, only add the indexes you definitely need early and wait with the rest until you're done importing. There are many use cases for a database like this, like using it behind an API to let users query data that would otherwise be close to impossible without a database such as this. We have augmented the database by adding some of the missing social layer, like which virtual asset service providers owns what accounts, but also knowledge of known criminal actors or otherwise high-risk accounts. Based on the data, we can also guess with some precision the nature of an account. For example, whether it's a high velocity hot wallet account for an exchange, or if it's an intermediary account used just to move money through a clean account prior to sending it to an exchange. One of the outputs of this is an advisory list, a list of accounts that are most likely involved with criminal finances of some sort. This list is available to, for example, exchanges, so they can withhold and file suspicious transaction reports. This advisory list grows as money are moved, and our monitoring tools use the graph to follow the money as it happens. One example of real-time monitoring is a phishing case where victims were targeted with spam messages sent both as memos in microtransactions on the blockchain itself and in emails. It lured the recipients into entering their account access information on a website promising big returns in a community reward program. After successfully acquiring users' account information, the account was drained one by one. This graph visualizes that activity. The accounts highlighted in purple drained the surrounding victim accounts that are highlighted in green. Then the funds were moved in batches through freshly created clean accounts, highlighted in yellow, to be laundered through various exchanges. Another example of using the graph database to unravel how the payments network was used to move illicit funds is the story of Plus Token. Plus Token was a successful Ponzi high-yield investment program running from 2018 to 19. During June of 2019, users started experiencing delays in funds withdrawals, but it abruptly stopped on June 30 when all interest payments stopped. According to data from several sources, the Ponzi scheme was successful in fleecing users of assets worth close to $3 billion, some of which were in XRP on the XRP Ledger. When accounts flagged in our database started moving money about a year after the Ponzi exit, we started investigating the connected accounts, providing us with the picture in this slide. All the larger scale dots in the perimeter are exchange accounts, but the huge masses of dots in the middle are accounts with its sole purpose to send money around to shuffle it and make it harder to trace. But using tools like Neo4j and the transactions and algorithms, it's quite easy to write queries that can find these networks. A third example on how we can use an algorithm to lighten the burden of connecting multiple individual cases based on the information we assign to the nodes in the graph. This graph visualizes all transactions to and from a select subset of accounts we have flagged. This means every node represents either an account belonging to an exchange that is used for laundering, a victim to a scam, or theft, or a bad actor collecting money from a victim or moving them around. The graph is highly connected because the same exchanges are used by many different bad actors. A victim could potentially also be a victim to multiple scams. So by removing victim and exchange nodes, we get a much cleaner graph where we can see the connections between the bad actor accounts alone. Now, with a cleaner graph only including transactions sent between bad actor accounts, we can see a lot of disconnected individual islands of connected nodes. Just zooming it in a bit for better visibility, the nodes and relations are still showing with the same visualization layout as before, but if I were to rerun the layout without the exchange supernodes affecting it, the individual islands would be pulling together. From a clean subgraph like this, I can run a weakly connected components community detection algorithm that basically identifies these groups of nodes that together form a disconnected component, or what I refer to as islands, and outputs a component ID for each node. Using this, it is extremely fast to identify whether several individual cases of scams or thefts are likely to be connected. In general, for graphs with billions of nodes, it is quite difficult to run algorithms on a full scale. So instead of running a community detection algorithm on all accounts and all transactions, it's great to be able to do cipher projections to make a smaller and relevant subgraph to do it on. As I have mainly worked with Neo4j 3.5, the database would simply crash when running out of memory. In the current graph data science libraries, most algorithms will do a memory estimation check before executing, which is really neat. So that was all from me. Thank you for listening. I will be here for a while to take questions, and I'll try to answer them to my best abilities. Thank you for listening.
Wow, what an incredible journey. So this is something that a very good use case of using the database, right? And so how long have you been using the database for?
Since 2018, 2019. Yeah.
Oh, wow. All right, so let's see if there is any questions for you, and make sure to ask any questions that you have for Thomas. All right, so we got one here from Michael Hunger. What kind of APIs do you offer on that database, Thomas?
Yeah, so right now we have an API for exchanges for an advisory list. So high risk accounts that are potentially involved in fraud. So that's a direct output from the database. From other APIs, we are building out a data API that is basically we're building out a data API for the entire blockchain, providing data that is hard to get from the blockchain itself. So that is trade data, that is ancestry information between accounts or balance changes over time and stuff like that. And we're using Neo4j for some of it, and then we're using other databases for other parts, such as time series databases for exchange information over time. So yeah.
All right. So you're kind of mixing them all together to get kind of the strength of every platform and working together.
Exactly. So where Neo4j or graph database is awesome for connected data or for finding relationships between data or running these algorithms, other databases are just far superior in other ways, of course.
All right. Well, thank you for talking with us. We'll have a short little break, and we will get back with our next speaker. All right. Thank you for joining us, Thomas.
Thank you for having me.
Goodbye.